In this lesson, we talk about a way to use tangent lines to approximate function values. And so let's look at this graph of sine of x. And here's the tangent line. The red line is the tangent line at 0. Here is the equation of the tangent line. So if we look at for each of these x values, we have these values of the tangent line, y equals x. So these are y values of the red line. Here are y values of the curved line. And let's look at how they compare. You need to compare the y values, because if we're going to make an approximation, we're approximating y values for one x value. How close are the y values? How good of an approximation is the tangent line to the function? So just think about this, true or false. The tangent line is a good approximation of the function. So now look at all the y values and decide whether that's a true or false statement. And we see sometimes the tangent line is a good approximation of the function. 0.3, 0.29, 0.5, 0.47, 0.79, 0.71. Well, this is not as good of an approximation. And here we have 1.5 and 1. So this is getting further away from the function. And we can see that in the graph. If we wanted to approximate the value of sine at 2 pi, the tangent line would be too far away and it wouldn't be a good approximation. So we see how tangent lines are good approximations of functions when you're trying to approximate values that are close to the point of tangency. Based on what we see here, approximate sine of 0.1. So we don't have a 0.1 in the table, but think about what is happening here, how these y values are, how they compare, and what would happen at 0.1. So if we look at this at 0.3, the tangent line is 0.3, and sine is almost 0.3. At 0.2, the tangent line is 0.2, sine is almost 0.2. So at 0.1, the tangent line is 0.1, and we would say that sine is approximately 0.1. So there's an approximation. We used what we saw in the table to approximate the value of sine at 0.1. What if we wanted to approximate sine of 1.5? And 1.5 is approximately pi over 2. So we're trying to approximate this y value, something close to that y value. What should we do to approximate this y value? And it turns out we should just draw or use another tangent line. So why don't we, instead of using the tangent line at x equals 0, we could use the tangent line at pi over 2. So this tangent line at pi over 2 well, I just noticed that this graph, the scale is off. This should be at 1, so let's just call that a 1. And that should be at -1. So let's just do that, because we know that that should be at 1. All right, so if we drew a tangent line at pi over 2, we know its value is 1 because that's, we know the y value at pi over 2 is 1, and that's a horizontal tangent line because it's at a maximum. So our tangent line would say that sine of 1.5 is approximately 1 if we use that tangent line. So there's an example of we choose a tangent line that has a point of tangency close to the x value that we want to approximate. So if we're going to make a tangent line, we need to have a function. And maybe you don't see the function. There's no equation here. Radical 14. Well, we could say that radical 14 is the y value of y equals radical x at x equals 14. So now if we think of this as being a function value for this function, now we have an equation and we can graph it. We can find a tangent line at a point close to 14. So let's think of the graph, and we have radical x, so it's going like this, and let's just say that we want to know the value, we want to know what's the y value at 14, what is radical 14. So the first step is decide where to put the tangent line. Why don't we choose a number close to 14 that is a square number, in this case because we're doing square root. And I'll just say choose an easy number to use in this, because if we drew this tangent line, we could say that the y value of the tangent line is close to the y value of the function. So step 1, choose easy number near 14, and we chose 16. Make a tangent line, equation of tangent line, so that's with the slope and point slope. So we have y equals x to the 1/2. Y prime equals 1/2 x to the negative 1/2, which is 1 over 2 radical x. So the negative exponent means write it as the reciprocal, and let's evaluate this at 16. We need the slope. The slope at 16, we're not going to find the slope at 14. We're going to find the slope to make the tangent line at 16. So I'm putting a 16 in there. 1 over 2 radical 16, and that'll give us 1 over 8. Then we'll have y minus y, m, x minus x. Again, we're not using 14 yet, we're still using 16 because we're making the tangent line at x equals 16. The y value at 16 is 4. Square root of 16 is 4. So we have a tangent line. Step 3, find the value of the tangent line at 14. So we're just finding the y value of the tangent line. That's what we see in the graph. We want to know the y value of the tangent line. What's the y value of the tangent line at 14? And then we'll say that the y value of the tangent line is close to the y value of the function. And we'll have 14 over 8, reduce it to 7 over 4, and then this is 8 over 4, so we'll get 15 over 4. All right, and then step 4, we can talk about the error. How close is the approximation to the actual value? And we say that the error, we could say radical 14, the actual value minus the approximate value, and then we do absolute value because we don't care if it's above or below, we're just saying how close is it. Alright, and we could talk about that being the error, but we can also talk about the percent error, and that's just going to be the error divided by the actual value. How far away is it from the actual value? And we get 0.0022 or 0.22%. Well, I guess this isn't actually percent error. We had to convert it to percent. So why don't we just say, we won't say percent error equals this. We'll put an arrow, and we'll just say to find the percent error, divide this, and then change the decimal into a percent. All right, here you have to identify a function to find the equation of the tangent line, and then also find a point, find an x value close to the desired x value. So pause the video and try this one. If we see something cubed, we could say that we're looking at x cubed evaluated at 2.13. So step 1, easy number, choose an easy number. What number is close to 2.13 that's easy to use? And then usually just an integer, so we'll choose 2. Tangent line. The slope. We need the slope of this, the derivative of this function. Y prime is 3x squared. Y prime evaluated at 2. 2 squared, we get 12. Point slope, y minus y equals mx minus x. We need the y value at 2. The y value at 2 is going to be 2 cubed, 8. Add 8. We have the tangent line, and then we the value of the tangent line is the approximation. So we're going to go y evaluated at 2.13 in this equation, 12 times 2.13 minus 16, and we get 9.56. And then we can look at the error. The error is the actual value minus the approximation, absolute value, and that is 0.104. And then the percent error is 0.104, the error, divided by the actual value. And if we wanted to leave that as an equal sign, we can just multiply by 100, and that'll change it into a percent. So here we get 1.07% error. And if we don't multiply by 100 and we don't want the percent error, then this would be called the relative error. Alright, now we have some more notation and vocabulary that go along with approximations, and these are called differentials. So we have a function and a tangent line. Let's just say that's 1 and 2. All right, so we have the point of tangency and how far we go out away from the point of tangency. Here we would call this the change in x. It's also dx. Now up here we have at the starting x value we have the starting y value, and then the ending x value we have the ending y value. So let's call this f of 1, and this is f of 2. Alright, so that is the change in y, delta y. But we also have the y value of the tangent line. So let's call that y of 2. So we have the tangent line, it has a y value, and we're going to call the change in the tangent line dy. So dy is called the differential of y. Dx is called the differential of x. Okay, and now let's remember that y prime is dy dx. Just two different notations for the derivative. But now let's look at, we already know that the differential of x is equal to the delta x, the change in x. They're equal. What does differential of y equal? It's not equal to delta y. So we can look over here and make a formula for dy by multiplying by the differential of x. So we'll have y prime times dx equals dy. So now we can find the differential of y by multiplying the differential of x times the derivative. And we did that just by multiplying both sides by the denominator. So we'll do another tangent line approximation. We'll also talk about the differentials. And go ahead and do this part on your own, pause the video, and then do as much of this as you can. So the cubed root graph goes like that, and we want to know the y value at 9. So also we have the cube root of 9. Well, that's just a y value of the cube root of x. So here's the function. We need the tangent line to this. Step 1 is choose easy x. And easy x next that's near 9. Well, 10 doesn't work because we're doing cube root, but 8 would be a good choice because it's a cube. So that's going to give us that point. We'll make a tangent line, and that tangent line is going to give us an approximation of the y value of the function at 9. The easy x is 8. All right. Tangent line. Find the slope, then do point slope. Remember that this is x to the 1/3, so we'll have y prime equals 1/3 x to the negative 2/3 using the power rule, multiply and subtract. This is going to be x to the 2/3. Let's evaluate that at 8. Y prime of 8. And this is going to be the cubed root and then square it. Cubed root of 8 squared. So 2 squared is 4. We get 1/12. Then we'll do the point slope. Y minus y, m, x minus x. And it's the x that we chose, and it's the y value at that x. So we put an 8 there. The y value is 2. Eight over 12, we'll get 4 over 8 over 12. And then we have to add 2, so that means we're adding 24 over 12. Let's just write it out so I don't make a mistake. Add 2 to both sides. This is equal to 2. We have 24 minus 8, so that's going to be 16 over 12. So y is 1/12 x plus 4/3. Okay, and then we want y value at 8. No, y value at 9. Y at 9 is 1/12 of 9 plus 4/3. We get 2 1/12. There's the approximation. Let's skip the error and we'll talk about the differentials and deltas. So if you spread it out a little bit, it's easier to see all the values. We have a tangent line at 8. And the actual change, this is going to be delta y, and then the change in the tangent line is going to be the differential of y. So we have a y value of the function and a y value of the tangent line. starting at 2, we're going to go up to the tangent line and also up to the function. The function value is approximately, well, it is exactly cubed root of 2. This is cubed root of 2. This is what we approximated. That's 2 and 1/12. So delta y is cube root of 2 minus 2. No, cube root of 8 minus 2. No, it's not. I'm sorry, cube root of 9. So let's make sure that's clear. At 8, the y value is 2. At 9, the y value is cube root of 9, and that's that y value. We also have at 9 the y value of the tangent line, and that's what we found right there. So if we want delta y, it's cube root of 9 minus 2. Delta y is cube root of 9 minus 2. Differential of y is 2 and 1/12 minus 2. So delta y is approximately 0.08, and dy, the differential of y, is 1/12, which equals 0.083 repeating. So these are the ones that require a little work, because over here we just go 9 minus 8 equals 1, and that's delta x, and that's also the differential of x. And we'll stop there.